Okay, this is Jack Jackson again, and this is part 4 of our series of lectures on developing the complex number system and basic operations. In this one, we're just going to kind of summarize some of the things we've done before, and I've got a few graphics that are going to be pretty useful for kind of keeping track of all this. So let's talk about the relationship among the 6 basic operations. So if we start with a set of natural numbers, which are just the counting numbers, then our most basic operation is addition. We can think of addition as just combining comparable groups and determining the amount of the combined group. It is closed for the whole numbers and closed for the natural numbers. If we repeat addition, then we get multiplication. Multiplication can be thought of as repeatedly adding the same number over and over again, or combining groups of the same size. Again, it's closed for the natural numbers and closed for the whole numbers. So, in its most basic form, multiplication is repeated addition. Then we can take repeated multiplication and make exponents, okay, or powers. Exponents or powers tell us that we repeatedly multiply the same number over and over again. It's closed for the whole numbers and the natural numbers. So we can think there's a natural order here. Addition is our most basic operation, multiplication is repeated addition, exponents are repeated multiplication. And as long as we stay in the natural numbers, and as long as we stay with just these 3 operations, everything's fine. We can add any 2 natural numbers, get a natural number, multiply any 2 natural numbers, get a natural number, and take any natural number to a natural number power and get a natural number. So everything's fine, except that the problem is that we want to be able to undo these operations. And so if we want to undo addition, that leads us to the inverse operation of subtraction. So subtraction can be thought of as solving for a missing add-in. Okay, we can define subtraction ultimately as adding the opposite, or additive inverse. Taking away and determining the amount remaining is a real-world model for that. And this forces us to increase our number system to the set of integers. Okay, and so we have our inverses here. These are inverse operations, and creating the inverse operation of addition forces us to not only make subtraction, but to widen and expand our number system. Now, we can also think of multiplication and doing its inverse, okay, which is division. We can also think of a repeating operation down here. We can repeatedly subtract, and we can think of division as repeatedly subtracting. So if we're dividing by 3, we're saying, okay, how many times can we subtract 3? To get down to 0. Okay, we can also think of division as multiplying by the reciprocal once we understand what a reciprocal is, a multiplicative inverse. Or we can think of it as solving a missing factor problem, and we're basically breaking into groups of equal size. One interpretation, we know how many groups we have, we want to determine the size of the group, and the other interpretation is we know the size of the group and we want to know how many groups. Those correspond to 2 missing factor problems. These are closed for the non-zero rationals. So what happens here again is if we want to undo multiplication, it leads us to division, but that leads us to problems that we can't do in the natural numbers or even in the integers. So we have to extend that number system out to the set of rational numbers, which we use a Q for quotient. The quotient's the answer to a division problem, so we use Q for quotient. If we want to repeatedly divide, or if we want to reverse exponents, then that leads us to the concept of a root or a radical. Okay, they can be expressed as fractional exponents, so they can be thought of as exponents, but fractional exponents. If we want to make it closed, we have to expand our number system beyond the natural numbers, actually beyond the integers, beyond the rationals, up to the reals, and even further all the way to the complex number system. Now there are a few exceptions. You can't divide by 0, so other than that the rationals are closed under division. And you can't raise 0 to a 0 power or 0 to a negative power either. And so that makes the roots closed, the complex numbers closed under the roots, except for those few exceptions. And so the complex number system is a very, very complete number system that has lots of good properties. And so we can see the relationship among these basic operations, and expanding them out forces us to expand what we mean by our number system. We also have an inherent order to our operations. Because exponents and radicals, because radicals are just really exponents in disguise, fractional exponents, we can think of those at the same level. Multiplication and division are at the same level because division can be thought of as multiplying by the reciprocal. And subtraction can be thought of as adding the opposite or adding the additive inverse. So really subtraction can be rewritten as addition, division can be rewritten as multiplication, and radicals can be rewritten as exponents. So then you're basically down to your three basic operations again: addition, multiplication, and exponents. In their most basic form, exponents are just repeated multiplication, which multiplication in turn is just repeated addition. So there's a natural order. You want to do your exponents first. It's the highest level of operation. Do it first. Then you want to do multiplication next, and then addition last. Now notice we've talked here about this. We've said multiplication is repeated addition. Well, that makes sense if the two numbers are natural numbers, or even if just the first number is a natural number, or one of the numbers is a natural number. But we've extended our idea of multiplication to make sense of things like a negative times a negative, or a fraction times a fraction, or whatever, even complex numbers. So we've come up with different ways of expanding our meaning of multiplication beyond repeated addition. But at its core, that's where it started, is repeated addition. And similarly, we expand our idea of exponents beyond just repeated multiplication to allow for things like integer exponents, zero exponents, fraction exponents. Okay? But still at its core, we can think of exponents as starting from repeated multiplication. Now sometimes you don't want to do things in the natural order, so you supersede that or replace that with grouping symbols. And notice we have different kinds of grouping symbols. Parentheses, brackets, and braces are really all the same thing in the terms of grouping symbols, and they're sometimes used for different levels of grouping within grouping, but basically they're just grouping symbols. It says do what's inside the parentheses, get it to a single number before you do anything else. But there are other types of grouping symbols that we use as well. A horizontal fraction line, not a slanted fraction line or a division symbol, but a horizontal fraction line is two things. It's a division symbol or fraction symbol, but it's also a grouping symbol. It says do whatever's in the numerator first, the top, get it to a single number, and get the bottom to a single number, do what's in the denominator first. Do those two things separately first, and then do your division. So it's a grouping symbol. Similarly, a radical, a square root, a cube root, or whatever, says do what's underneath the radical, sometimes called the radicand. Take that and figure out that radicand is a single number, then take the root. Absolute value. It says take whatever's inside that absolute value bars, get it down to a single number, then take the absolute value. So these last three symbols are more than just grouping symbols, but they are grouping symbols, and there may be some others as well. Okay, so we start building up our number system. The most basic numbers are called natural numbers. The natural numbers are closed under addition, multiplication, and exponents. And they can be represented as dots along a straight line. These dots go forever to the right, but not forever to the left, and there are definitely some empty spaces between these. We use this symbol for n for the natural numbers, and of course in our Hindu Arabic numerals there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth. And of course those words are the English words for those numbers. If we take the natural numbers and we throw in another number, 0, that adds one more dot here to on the left end of our number line, and this forms a set of whole numbers. Notice that the natural numbers are all also whole numbers. There's one whole number that's not a natural number, 0, but all the other natural numbers, all the natural numbers are whole numbers. So the natural numbers are a subset of the whole numbers, which is illustrated by this diagram. This kind of diagram is called a Venn diagram, V-E-N-N. Next, we expand our number system out a little bit more, and we say, oh, well, if we can go forever to the right, we can also go forever to the left and extend this out, and then we can get the integers. Okay, so we want to undo addition, that is subtract or solve missing add-in problems, meaning we must extend the numbers to the set of the integers, which will include the whole numbers and their additive inverses. So not only do we include 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., we also include -1, -2, -3, and so forth. Now, the integers then include the whole numbers, which include the natural numbers. So the natural numbers are a subset of the whole numbers, which are a subset of the integers. And the integers, in turn, are a subset of a set called the rational numbers. Rational numbers are numbers of the form, or that can be put in the form, p over q, where p and q are integers, but the q can't be 0. And that turns out, as we've seen, to be exactly the same set as the set of terminating or repeating decimal numbers. So if we want to undo multiplication, that is, we want to divide or solve missing factor problems, we must extend the numbers, the integers, to a larger set of numbers, the set of rational numbers, which give us fractions. And these are possibly might be in other forms, such as percents or decimals or ratios. Now at this point we have filled in a lot of the spaces between the integers on a number line, and in fact in between any two rational numbers there's always another rational number, say for example halfway between the two. But there's still a lot of missing numbers still on a number line. And so if we want to fill in a solid number line like we see up here, where now not only do we have the negatives going left and the positives right here, but we also, with 0 in the middle, we also have filled in the entire solid number line in the middle. Okay, and this gives us the set of real numbers, and this is all decimal numbers. So we take the real numbers and take away the rationals. This gives us the non-terminating, non-repeating decimal numbers. That's called the set of irrational numbers. And if you union the set of irrationals and rationals, you get the set of reals. So notice that the irrationals are exactly the real numbers that are not rational. Okay, and so we still have a subset way of doing it. We start with the natural numbers. We threw in one extra number, 0, to get the whole numbers. We take the whole numbers, we throw in the additive inverses. Now we have the integers. Now we take the integers and we also throw in the other numbers that can be terminating or repeating decimals, and we have the rational numbers. Then we throw in the other decimal numbers, the ones that are not terminating, not repeating, and now we have the real numbers. Okay, and so these correspond to points on a number line. There's any line, there's a one-to-one correspondence between the real numbers and the points on that line. Now, we go out one more step and we get what are called the complex numbers. And the complex numbers are the real numbers along with some more numbers, the non-real complex numbers. And their numbers are the form a plus bi, where a and b are real numbers, and I is the principal square root of -1. It's our imaginary unit. Now, of course, if the b is 0, we just get real numbers, so the real numbers are complex numbers. If the A is 0 and B is not 0, you get numbers of the form BI, where B is a real number but not 0. Those are called the imaginary numbers, or pure imaginary numbers. Then we also have numbers in the complex numbers that are neither imaginary nor real, like 3 plus 2i is neither real nor imaginary. Some books will call that imaginary, but that's not really a proper way of doing this. Properly speaking, 3 plus 2i is neither real nor imaginary. And so here we have the complex number system, and this diagram gives you a relationship among all of these. We can represent the points on the complex number system not on a number line, but in a plane, and we can graph those. So if we graph the ordered pair 1, 3, for example, in a plane, that represents the point 1 plus 3i. And so there we have our complex number system. And how do we see that it's a natural extension of just taking our basic operations and extending them out. In this course, we will always be working, well, almost always be working within the complex number system. And more often, we will mostly be working within the real system, and even more often than that, be working with rationals and even integers most of the time. So, we won't always be going all the way out to the complex number system, but we do need to know that that's there, and it is needed if we want to be able to do all of our operations in general.